Welcome to Lecture 11 for Chemistry 141.
Let's talk briefly about our transition metals. With transition metals, electron configurations for the transition metals are not always what you'd expect. We look here, we go across the periodic table, and I've got 4s2, 3d1, then 4s2, 3d2, 4s2, 3d3, 4s1, 3d5. So things all of a sudden changed right here with chromium. But notice what's happened. We've taken one of our s electrons and moved it up into the d. We would expect this to be 4s2, 3d4, but as it turns out, when we half fill a subshell, we lower its energy. And so rather than having 4s2, 3d4 with a full shell and a not half or anything shell, instead we go to 4s1, a half-filled shell, 3d5, which is also a half-filled shell. So that configuration there lowers the energy of the atom just a little bit more than this one here. So this is why that anomaly exists. And then we get back to 4s2, 3d5, 3d6, 3d7, 3d8, and then we have another situation here at copper where it's 4s1, 3d10. We would have expected copper to be 4s2, 3d9. However, by taking one of those s electrons and putting it into the 3d, we get a half-filled shell there and then a filled d shell there. And so we have two things, again, that help lower the energy rather than just one. And so this is what the atom does, and it's just another one of those anomalies. If we look at period 5, we see that the exceptions are even greater. So things to keep in mind, some of these that we just talked about. The NS, like the 4s and the 3d orbitals, are close in energy. The 5s and the 4d orbitals are even closer in energy. And we do get a small amount of stabilization or energy lowering happening as a result of either a half-filled or a completely filled orbital. And so what this means is that electrons will rearrange to half-fill an orbital if possible, because this lowers the energy of the atom overall. And so those electrons do bounce back and forth a little bit. The F block elements are even stranger than the D block elements, but we're not going to worry about those. We don't really do anything with F block electron configurations in this course.
Is electron configuration and properties. And if you take a look at kind of the history of how things developed as far as our knowledge of electron configuration, our knowledge of the periodic table, they really started developing separately. Periodic table starting in the late 1800s, and then of course electron configuration, quantum mechanics starting really in the early 1900s. And so eventually we started bringing these things together. Now, one of the things that people noticed was that the non-reactivity of the noble gases are group 8A. And so they're called the noble gases because of their stability and reluctance to react with other elements. And so if we take a look at the electron configuration for all of the noble gases, we notice that they all have 8 valence electrons, with the exception of helium, of course, which only has 2 electrons total. But everything below helium has an electron configuration of ns2, np6, where n is the period that noble gas is in. So the implication is that elements will lose or gain electrons in order to achieve the same configuration as a noble gas, either by losing electrons or by gaining electrons. And this is one of the reasons that so many elements are more stable as ions than in their native elemental form. Now, if we look at the periodic table, we really have 3 types of elements. We have metals, which have a tendency to lose electrons and thus become cations. We have our nonmetals, and they have a tendency to gain electrons and thus becoming anions. Metals lose electrons because they're going backwards on the periodic table to get to the closest noble gas. Nonmetals are gaining electrons to make it to the next noble gas that tends to be closest to them. And we've also got our semi-metals, which are also called metalloids. That's a term that you hear more often now. They don't generally gain or lose electrons and don't actually form ions very often at all. And when they want to form compounds, they tend to share electrons, and that's something that we're going to learn about later on in this course. Let's take a look at the periodic table here. And what we see is some different areas here. We've got our metals here. Our metals are in this big block here, in this kind of light cream grayish color here. And then of course all these guys down here, these are also metals. So you can see the periodic table is really dominated by metals. We've got our nonmetals here in kind of this light blue stair step here, right there. So those are our nonmetals. And then we've got this little line of our semi-metals. They kind of form that barrier between the metals and the nonmetals. And the semi-metals, the metalloids, are really kind of interesting because they share properties of both the metals and the nonmetals. And they're really kind of a good read, and your book does a nice job of going over those. Some of the other things that we need to be aware of in the periodic table are some of the names of some of the more common groups that we deal with. The first is going to be the alkali metals here, and they comprise group 1A here. So those are our alkali metals. We have our alkaline earth metals here in group 2A. And then we've got our halogens here in group 7. So those are our halogens. So we only point those out because those are very typical elements that we refer to as a whole group when we're looking at the chemistry of an entire group. And so these are very common elements that we do that with. So if we look at these named groups, which are kind of special, we do have our alkali metals. They do have a general configuration of NS1, so they have one s electron. So they tend to lose that one electron and form +1 ions. And so when they lose that one electron, what's left is a noble gas configuration. And so that's what they lose and form the +1 ion. Our alkaline earth metals have a general configuration of NS2. They tend to lose 2 electrons and form +2 ions. And then our halogens, they're on the other side, and they're actually closer to the noble gases by gaining electrons. And so your halogens in group 7 will gain an electron and form -1 ions. And we can take a look at some trends here that we see in forming ions. For a lot of the main group elements, we can use their position in the periodic table to determine their preferred charge. And so if we look at group 1A, we see that they all have that configuration of NS1. They're all going to lose 1 electron, and as a result, they all have a +1 charge. We look at group 2A. They all have an NS2 configuration, and they're going to lose those 2 electrons to get a noble gas configuration, and they all have a +2 charge. As soon as you start getting over here on this other side, things start changing a little bit. Group 3A, one of the most typical there is aluminum, and it tends to lose 3 electrons, and so forming aluminum 3+. Boron here doesn't really lose any of the electrons, and then the elements down here tend to do some funny things as well. One of the things they do, however, is lose 3 electrons, but they may lose more. Our group 4A, you'll notice, doesn't list any ions in here at all. So if we think about group 1A losing an electron, 2A losing 2 electrons, 3A losing 3 electrons, it's because that's the fewest number of electrons that it can either lose or gain, and gain a noble gas configuration. If we think about group 1A, they could either lose 1 electron or gain 7, and it's always easier to do the smaller number, so it's easier to lose 1. Group 2A can either lose those 2 electrons or gain another 6 to get a noble gas configuration. Losing 2 is going to be easier, and so they form 2+ charges. When we get to the 4A, well, they've got 4 valence electrons, so they can either lose 4 or gain 4. Which of those is easier? Well, we don't know, and they don't know either, so they don't do it. So they don't tend to form charges when they're forming compounds. So instead, they share their electrons, and we're going to talk about that later. Now we're starting to get into group 5A here, and now we're closer to gaining closer to a noble gas by gaining electrons than losing them. Something like nitrogen in group 5A has 5 valence electrons, so it can either gain 3 or lose 5 electrons. It's going to be easier to gain 3, and when it does that, it gets a 3 minus charge. Group 6A, it's better for them to gain 2, so they have a 2 minus charge, and then group 7A here, it's easier for them to gain 1, and they get a minus 1 charge. So really, if you look at the trends here, we have plus 1, plus 2, plus 3, skip, minus 3, minus 2, minus 1. So it kind of goes up a ladder and then down a ladder. Plus 1, plus 2, plus 3, skip, minus 3, minus 2, minus 1. We see trends also in the periodic table. So we didn't, even though we only organized the periodic table by chemical properties, we also found that there's trends in atomic properties. Some of those periodic trends involve atomic radius and effective nuclear charge. For atomic radius, we found that there's lots of different ways of measuring and reporting the atomic radius. A lot of times we use either the van der Waals radius or what we just call the atomic radius, which is an average of all the different techniques for measuring atomic radii. So the van der Waals radius involves using solids primarily, and so really what we're looking at is this distance between the nuclei of a couple of atoms, and by cutting that in half, you can then get the atomic radius. If you have a covalent radius here where you can see the atoms themselves are kind of mushed into each other, we can still find the distance between the nuclei there, and again cut it in half and get a radius there. And so we look at all the different techniques. They all make different assumptions, and a lot of times they'll get different values. They're always going to be close. And so a lot of times we use this atomic radius method, which is usually just an average of all those different techniques. We can look at some of the trends that we have. And if we take a look at going from lithium to potassium to rubidium to cesium, we have a general increase of the periodic table as we go down a group. And lithium there is period 2, sodium is period 3, potassium is period 4, rubidium is period 5, cesium period 6. So as we're going down a group, so we're going down group 1A, it's all group 1A, we see that the atomic radius on the y-axis there is getting larger and larger. And we see that if we went down over to group 2A, which would be the second dot right here, it's also getting bigger as we go down that group. So as we go down a group, atomic radius increases. And this should make sense that this is happening because as you go down a group, you're adding a whole nother shell onto the outside of that atom. So it gets bigger. Now the one that's kind of weird is atomic radius decreases as we go down or across a period. So as we go down a group, so down group 1A here, across period 2, we see a general decrease in the atomic radius. Well, how, as we go down, even though we're adding an electron and adding a proton, does the radius get smaller? The atom should get bigger. We're putting more stuff in it. Why doesn't it get bigger? Well, let's take a look. So the answer lies in effective nuclear charge. If we take a look at our core electrons, they're shielding outer electrons from feeling the full effect of the positive charge in the nucleus. And so electrons in an outer shell do not shield each other. So as we move across the periodic table, what we're adding, as far as electrons, is we're adding electrons into the same shell. So the number of protons is going up in the nucleus, but the shielding does not change. As a result, the effective nuclear charge from the nucleus is going up, and attraction between the nucleus and the electrons is going to increase. This has the effect of decreasing the atomic radius. Let's take a look at a little graphic that shows how that works. So we see here, this is just for a lithium atom. We've got our 1s electron here and another 1s electron here. So those are in the core. Our nucleus here has three protons in it, and so it has a 3+ charge. Now it's a little bit of an approximation, but we can see what the effective Z felt by this outer electron, this 2s electron, is by taking the number of positive charges put out by the nucleus minus the number of shielding electrons. And so we've got 3 pluses from the nucleus, 2 minuses shielding it, and so really what that outer electron is feeling is just that single 1 plus. So that electron in the 2s1 or in the 2s orbital there is really only feeling like there's a 1 plus nucleus in there, so it doesn't attract it nearly as much. Now if we were to go to beryllium, what we'd find is we would then have a 4+ charge in the nucleus. We would still only have a -2 for the shielding electrons, and that would about equal 2+. So my Z effective now has gone up for beryllium, and that's going to attract those valence electrons in closer and make my atomic radius a little smaller. And this just keeps going as we go across the periodic table. Now if we look at the transition metals, what we notice is that the atomic radius stays fairly constant. It's not constant, but it doesn't change by nearly as much as what the other elements do as you go across the table. Now the reason for this is because as you move across the table through the transition metals, your additional electrons is filling an n-1 d orbital. And so that's going into a core shell. And so as a result, the shielding is increased. Now you're also adding a proton into the nucleus. So you're adding a shielding electron, but then you're also adding a proton. And so as a result, your Z effective is pretty much the same as you go from element to element in the transition metals. Again, it's not exactly the same, but the atomic radius for your transition metals as you go across the periodic table actually stay fairly consistent with each other. Now we can also look at magnetic properties of both atoms and ions here. We've got two different terms that we use to look at magnetic properties. One of those is paramagnetic, and this is where you have unpaired electrons in the orbitals. And then we've got diamagnetic, and this is where all electrons are paired. It's very easy to confuse diamagnetic and paramagnetic because a lot of people think that paramagnetic means that your electrons are paired, but it's a different type of pair. The easiest way I've always found to think about it is diamagnetic. Dia means two. Two is a pair. Electrons are paired. So diamagnetic is where electrons are paired. Let's take a look at each one of those terms individually. So paramagnetic, if you have a paramagnetic atom or ion, what we find is that it is attracted to an external magnetic field. Let's take a look at a silver atom. If we look at the electron configuration of a silver atom, its electron configuration is krypton 5s1 4d10. We can write the orbital diagram, and it looks something like this. We see we've got our 5s1 here and our 4d10 right in there. And so this would be paramagnetic. Now if we were to have our Ag+, the electron that's going to come out is the electron with the highest n level. That would be our 5s1, so that's going to go away. So Ag+ would be krypton 4d10, and this electron would go away, and we're left with a diamagnetic ion. So silver atom is paramagnetic, silver ion is diamagnetic. Let's take a look at diamagnetic, and we'll use zinc to get our diagrams on here. But a diamagnetic atom or ion has no attraction for an external magnetic field. So let's compare a zinc atom and a zinc ion. So if we look at a zinc atom, we see that we've got everything paired up there. I've got 2 in the 4s and all pairs here in the D because it's a 4s2 3d10 configuration. If we look at our zinc ion, well, our zinc 2 plus, so I lost 2 electrons and they came out of the 4s there. So all I have is 4s0, or just don't write it, 3d10, which still has all of my electrons paired. So the zinc 2 plus ion is still considered to be diamagnetic. Now, one thing that's very important about is if the electrons did not come out of the s orbital, then they would have come out of these d orbitals here, would have left me with 2 electrons hanging there, and those 2 electrons would be back there, but this would have shown that the ion, zinc 2 plus ion, would actually be paramagnetic, but it's not. It's diamagnetic. So this indicates that these 2 electrons right here do come out of the 4s and not out of the 3d. Well, that finishes out Lecture 11. I hope you found this material useful. And as always, if you have any questions, make sure you contact us.